In physics, an inverse square law is any physical law stating that a specified physical quantity or intensity is inversely proportional to the square of the distance from the source of that physical quantity. In equation form, the divergence of a vector field which is the resultant of radial inverse square law fields with respect to one or more sources is everywhere proportional to the strength of the local sources, and hence zero outside sources. Newton's law of universal gravitation follows an inverse square law, as do the effects of electric, magnetic, light, sound, and radiation phenomena. Justification: the inverse square law generally applies when some force, energy, or other conserved quantity is evenly radiated outward from a point source in three-dimensional space. Since the surface area of a sphere is proportional to the square of the radius, as the emitted radiation gets further from the source, it is spread out over an area that is increasing in proportion to the square of the distance from the source. Hence, the intensity of radiation passing through any unit area is inversely proportional to the square of the distance from the point source. Gauss's law applies to, and can be used with any physical quantity that acts in accord to, the inverse square relationship. Occurrences: gravitation. Gravitation is the attraction of two objects with mass. Newton's law states, the gravitational attraction force between two-point masses is directly proportional to the product of their masses and inversely proportional to the square of their separation distance. The force is always attractive and acts along the line joining them. If the distribution of matter in each body is spherically symmetric, then the objects can be treated as point masses without approximation, as shown in the shell theorem. Otherwise, if we want to calculate the attraction between massive bodies, we need to add all the point-point attraction forces vectorially and the net attraction might not be exact inverse square. However, if the separation between the massive bodies is much larger compared to their sizes, then to a good approximation, it is reasonable to treat the masses as point mass while calculating the gravitational force. As the law of gravitation, this law was suggested in 1645 by Ismail Bolyaldus. But Bolyaldus did not accept Kepler unregistered trademark S second and third laws, nor did he appreciate Christian Huygens unregistered trademark S solution for circular motion. Indeed, Bolyaldus maintained the sun's force was attractive at aphelion and repulsive at perihelion. Robert Hooke and Giovanni Alfonso Borelli both expounded gravitation in 1666 as an attractive force. Hooke's 1670 Gresham lecture explained that gravitation applied to all celestial bodies, and added the principles that the gravitating power decreases with distance and that in the absence of any such power bodies move in straight lines. By 1679, Hooke thought gravitation had inverse square dependence and communicated this in a letter to Isaac Newton. Hooke remained bitter about Newton claiming the invention of this principle, even though Newton's Principia acknowledged that Hooke, along with Wren and Halley, had separately appreciated the inverse square law in the solar system, as well as giving some credit to Bolyaldus. Electrostatics, the force of attraction or repulsion between two electrically charged particles, in addition to being directly proportional to the product of the electric charges, is inversely proportional to the square of the distance between them. This is known as Coulomb's law. The deviation of the exponent from 2 is less than 1 part in 10^15. Light and other electromagnetic radiation, the intensity of light or other linear waves radiating from a point source is inversely proportional to the square of the distance from the source. So an object twice as far away receives only 1/4 the energy. More generally, the irradiance, that is, the intensity, of a spherical wavefront varies inversely with the square of the distance from the source. For example, the intensity of radiation from the Sun is 9126 watts per square meter at the distance of Mercury. But only 1367 watts per square meter at the distance of Earth. An approximate threefold increase in distance results in an approximate ninefold decrease in intensity of radiation. For non-isotropic radiators such as parabolic antennas, headlights, and lasers, the effective origin is located far behind the beam aperture. If you are close to the origin, you don't have to go far to double the radius, so the signal drops quickly. When you are far from the origin and still have a strong mu signal, like with a laser, You have to travel very far to double the radius and reduce the signal. This means you have a stronger signal or have antenna gain in the direction of the narrow beam relative to a wide beam in all directions of an isotropic antenna. In photography and theatrical lighting, the inverse square law is used to determine the fall-off, or the difference in illumination on a subject as it moves closer to or further from the light source. For quick approximations, it is enough to remember that doubling the distance reduces illumination to 1/4. Or similarly, to halve the illumination increase the distance by a factor of 1.4, and to double illumination, reduce the distance to 0.7. When the illuminant is not a point source, the inverse square rule is often still a useful approximation. When the size of the light source is less than 1/5 of the distance to the subject, the calculation error is less than 1%. The fractional reduction in electromagnetic fluence for indirectly ionizing radiation with increasing distance from a point source can be calculated using the inverse square law. Since emissions from a point source have radial directions, they intercept at a perpendicular incidence. The area of such a shell is 4I/R2, where R is the radial distance from the center. The law is particularly important in diagnostic radiography and radiotherapy treatment planning, though this proportionality does not hold in practical situations unless source dimensions are much smaller than the distance. As stated in Fourier theory of heat, as the point source's magnification by distances, its radiation is dilute proportional to the sin of the angle of the increasing circumference arc from the point of origin. Example: let the total power radiated from a point source, for example, an omnidirectional isotropic antenna, be P. At large distances from the source, this power is distributed over larger and larger spherical surfaces as the distance from the source increases. Since the surface area of a sphere of radius r is or equals a 4I/R2, then intensity A of radiation at distance r is. The energy or intensity decreases as the distance r is doubled. Measured in decibel, it would decrease by 6.02 a decibel per doubling of distance. Acoustics: in acoustics, one usually measures the sound pressure at a given distance r from the source using the 1 per Rankine law. Since intensity is proportional to the square of pressure or amplitude, this is just a variation on the inverse square law. Example: in acoustics, the sound pressure of a spherical wavefront radiating from a point source decreases by 50% as the distance r is doubled. Measured in decibel, the decrease is still 6.02 decibels, since decibel represents an intensity ratio. The behavior is not inverse square, but is inverse proportional. The same is true for the component of particle velocity that is in phase with the instantaneous sound pressure. In the near field is a quadrature component of the particle velocity that is 90 degree out of phase with the sound pressure and does not contribute to the time averaged energy or the intensity of the sound. The sound intensity is the product of the RMS sound pressure and the in-phase component of the RMS particle velocity, both of which are inverse proportional. Accordingly, the intensity follows an inverse square behavior. Field theory interpretation: for an rotational vector field in three-dimensional space, the inverse square law corresponds to the property that the divergence is zero outside the source. This can be generalized to higher dimensions. Generally, for an rotational vector field in n-dimensional Euclidean space, the intensity A of the vector field falls off with the distance of following the inversive power law, given that the space outside the source is divergence-free. History: John Dumbleton of the 14th century Oxford calculators, was one of the first to express functional relationships in graphical form. He gave a proof of the mean speed theorem stating that the latitude of a uniformly difform movement corresponds to the degree of the midpoint, and used this method to study the quantitative decrease in intensity of illumination in his Summa Logicae Philosophiae Naturalis, stating that it was not linearly proportional to the distance, but was unable to expose the inverse square law. In Proposition 9 of Book 1 in his book Ad Vitelionum Parallelipimena, Cubus Astronomiae Pars Optica Tradita, the astronomer Johannes Kepler argued that the spreading of light from a point source obeys an inverse square law. Original: Sic et se habent spherici superficies, cubus origo lucis pro centro est, amplia ad angustionem. Ita se habet fortitudos densitas lucis radiorum in angustiori, adilam in laxiori spherica, hoc est, conversim. Nam per 6. 7 tantundum lucis ist in angustiori spherica superficie, quantum infusior, tanto ergo alista patior and densior quam hic. Translation: just as the ratio of spherical surfaces, for which the source of light is the center, is from the wider to the narrower, so the density or fortitude of the rays of light in the narrower space, towards the more spacious spherical surfaces, that is, inversely. For according to Propositions 6 and 7, there is as much light in the narrower spherical surface, as in the wider, thus it is as much more compressed and dense here than there. In 1645 in his book Astronomia Philolaica a Euro, the French astronomer Ismaël Boulildus refuted Johannes Kepler's suggestion that gravity weakens as the inverse of the distance. Instead, Boulildus argued, gravity weakens as the inverse square of the distance. Original, Virtus autumnilla, quae sol penditsa harpagat planetas, corporalis curiipsi pro manibus est, lineis rectus in omnem mundi amplitudinem emissa quasi species salis cum alias corpor rotata, cum ergo sit corporalis imminuita, and extenuta in maiori spatio and intervallo, ratio autem huius imminutionis idem est, ac luminus, in rationem pe dupla intervallorum, sed diversa. Translation: as for the power by which the sun seizes or holds the planets, and which, being corporeal, functions in the manner of hands, it is emitted in straight lines throughout the whole extent of the world, and like the species of the sun, it turns with the body of the sun. Now, seeing that it is corporeal, it becomes weaker and attenuated at a greater distance or interval, and the ratio of its decrease in strength is the same as in the case of light, namely, the duplicate proportion, but inversely, of the distances, that is, 1/d squared. In England, the Anglican bishop Seth Ward publicised the ideas of Boulildus in his critique in Ismaelis Boulildi Astronomiae Philolaicae Fundamenta Inquisitio Brevis and publicised the planetary astronomy of Kepler in his book Astronomia Geometrica. In 1663–1664, the English scientist Robert Hooke was writing his book Micrographia, in which he discussed, among other things, the relation between the height of the atmosphere and the barometric pressure at the surface. Since the atmosphere surrounds the Earth, which itself is a sphere, the volume of atmosphere bearing on any unit area of the Earth's surface is a truncated cone. Although the volume of a cone is proportional to the cube of its height, Hooke argued that the air's pressure at the Earth's surface is instead proportional to the height of the atmosphere because gravity diminishes with altitude. Although Hooke did not explicitly state so, the relation that he proposed would be true only if gravity decreases as the inverse square of the distance from the Earth's center. See also, flux, Gauss's law, Kepler's first law, telecommunications, particularly, William Thomson, first Baron Kelvin, power-aware routing protocols. Inverse proportionality, multiplicative inverse, references. This article incorporates a public domain material from the General Services Administration document Federal Standard 1037-C. External links, damping of sound level with distance, sound pressure P in the inverse distance law 1 per Rankine, inverse square law on radiation protection by inactive.